Okay, good morning, ladies and gentlemen. Today we are going to officially start our GLM course. The GLM, what is GLM? What is this type of models? But GLM is actually a class of models that embraces many models that you probably have heard of. For instance, the classical linear regression model that you have already seen is a special case of the GLM class. Logistic regression, Poisson regression, um, gamma regression. There's a many different models that all can be framed within this general family. And therefore, whatever methods you develop, for instance, for fitting these models will be applicable to each of these individual cases of the family. Now we are going to start the courses. We're going to take the course. We're going to take two lectures to discuss some topics in statistical inference. Why we are doing that? Well, it's a very important domain in statistics. It's a domain that I find particularly fascinating because if you want statistical inference, you can see it as the foundation of the entire domain of statistics. Statistical inference gives us the tools, the principles that we need to use if we want to learn from data, how we can extract value from data. And we're going to take two lectures, it's some time, but I do that because it's not only that all these concepts are going to be later fundamental when we start studying the GLM class of models, but these concepts are going to be fundamental in all other courses of statistics you can potentially take. These are the same principles that you're going to find again when you study hierarchical models, when you study time series, when you study whatever model, whatever many of the statistical tools that you're going to see later on are going to be based on these principles of statistical inference. This is actually a very interesting domain. So let us start very simple. We're going to start from the basics and we are going to build up towards more complex concepts. The basic idea behind our profession, statistics, is the idea of randomness. And you may ask yourself, well, what is randomness? Actually, well, randomness is the occurrence of event for which no final cause is found. Is when events happen and there is not a deterministic reason for that. And it is a very important concept in nature and in science. If you think, for instance, about physics, probably all of you have already heard about something called quantum mechanics. And that's our best theory to understand nature at very small scales. We are talking here about atoms. We are talking here about particles. And when you study the world at these very small scales, very weird things start happening. And now, for the first time, we do have the technology to do that. You probably all have heard about the Large Hadron Collider here in Europe, this particle accelerator, where when you start studying how the world functions at this very small scale, determinism, as we see frequently in our normal life, completely vanish. We can only talk about probabilities. You cannot precisely determine in which point in a space a given particle is going to be, but you can just calculate the probability that it will be there. So at this very small scale, the fabric of reality is basically probabilistic. Randomness rules. Think about biology. For instance, if you look around, you see a huge diversity of life in our planet. Now, from where all this diversity emanates, where basically there are two main factors. One factor is, again, random mutations in the genetic code. The second factor is natural selection. And we are now in the middle of this pandemic, and we are all hearing about different variants of the virus. We have the Brazilian variant, the South African variant, the British variant. And again, from where all this emanates is from random mutations in the genetic code of the virus. So also in biology, randomness plays a very important role, but also in psychology, in almost every domain of science. So we are forced, we are confronted with randomness. We need to make sense of it. And the best tools we have to do so is mathematics, is statistics, is probability. And the basic concepts behind the basic tools that we have to make sense of randomness are probability distributions. So let's suppose we're going to do now a thought experiment. Suppose that you want to assess the intelligence of a group of children. And there are many ways of doing that, but we have typically this kind of IQ tests, IQ tests, they are some kind of rating scales that we use to assess the intelligence of individuals. Let us say that we have gathered information about the IQ score of 10,000 children. Then we can just represent this data in a graphical way using a histogram. And we are going to use a histogram with a class width of 10 IQ points. So every interval over here is 10 points wide. And the height of the bar here is the frequency of individuals that are in this class. So for instance, you have here the amount of individuals of the frequency of the individuals that have an IQ score between, let's say, 90 and 100. Now, suppose that you start gathering more information about more children. So you have this student, but not this study, but not with data on 10,000 children, but on 50,000 children, on 100,000 children, and so on. It's a conceptual experiment. It's not a real experiment. If the number of observations start increasing, you will see, well, indefinitely, if you really increase considerably the number of individuals, the number of children in your study, then the class width of your histogram can become smaller and smaller and smaller. And if you keep going in that process, at the end of this process, you will identify some kind of limit, a smooth curve. It arises from the histogram. In this case, we have it over here. And what statisticians have done over the centuries to try to create mathematical models that help them to describe these specific shapes. Now, you may get different shapes when you do this, depending on the phenomenon that you are studying. So statisticians have been forced and mathematicians have been forced to create different models to account for these different shapes they observe in nature. And one of these models is the so-called normal distribution, is the bell shape, as they call it. And what is the normal distribution? Well, it's a very elegant mathematical model. And there are many nice characteristics. First, look at the formula for the normal distribution over here. It's a very simple mathematical expression. It's just a couple of centimeters wide. And it depends only on two parameters, the mean and the standard deviation. So if you give me the mean and you give me the standard deviation, I will be able to just draw the curve exactly. It's a very elegant shape. It's this kind of bell shape. It's symmetric. That means that if you go to the center of the distribution and you look to the right or you look to the left, you are going to observe the same thing. It's the same shape. You have that the mode, the median, and the mean of the distributions, all of them are equal. So it's a very nice mathematical object. You can work with it very easily. You can obtain mathematical results very easily with the normal distribution. And if you have a random phenomenon, you are studying, for instance, IQ scores, and you know that the model, the normal model is a good model to describe the IQ scores, to describe the histogram of the IQ scores, then immediately you can make a lot of statements about this random phenomenon, about the IQ scores. For instance, you will know that almost all the individuals in the population will lie between two standard deviations of the mean. So you may have individuals that have an IQ score larger than two standard deviation the average or smaller than two standard deviation the average, but this is very unlikely. So most individuals will concentrate around the mean. Now, have you ever asked yourself why they call it the normal distribution? Well, this dates back a couple of centuries. Actually, in this 18th century, mathematicians started to see that many phenomena in nature follow this pattern. They follow this bell shape. For instance, if you got information about the maximum temperature on August 5th in the build, and you construct a histogram over the years, you will see that it follows this kind of pattern. If you study body length, if you study the intelligence measured by the IQ score, you will see that if you made a histogram, it follow this pattern. And the question was, why? Well, they observed it so much that they started thinking, well, this is normal. This is the normal way nature functions. But they didn't have a clear idea of why. And we will see later on in our lecture today some kind of heuristic explanation about the prevalence of the normal distribution in nature. But let's postpone this for a second. And well, why do we need a theoretical model in the first place? Why we just don't work with the histograms? Why the frequency distributions? Why do we need to create these mathematical models? And the answer to this question is very simple. It allows to calculate probabilities. And probabilities is what probabilities are our best way to quantify uncertainty. And in science, uncertainty is everything. Scientists are almost never absolutely sure about anything. There is always certain level of uncertainty, and probabilities allow us to quantify that. And you cannot do that just with a histogram. I mean, you need a theoretical model that allows you to do any kind of funny, useful, fun calculations. So suppose that you're studying, for instance, the Stanford Binet IQ scores. This is one of the scales we use to measure intelligence. Now, by construction, this scale has an average of 100 points and a standard deviation of 15 points. So by construction, the average IQ score of individuals in a population is 100 and the standard deviation is 15. They are standardized in that way. And we have, you can see that IQ scores follow a normal distribution. The latent mechanism that generate these scores can be modeled by a normal distribution. And now, once we have that, we can do any kind of calculations. For instance, you may assess what is the probability. If I choose an individual randomly in the population, what is the probability that he or she will have an IQ score between 97 and 115? Well, if the Q score follows a normal distribution, then you can calculate that probability just calculating the area under the curve. So here you have your interval, 97, 115. Here you have your normal distribution over here. And then the area under the curve is the probability that in a randomly selected individual is going to have an IQ score in this range. It's the probability over here. And you can see that's about 40% of the population. Suppose that you are interested in knowing what is the probability that an individual selected randomly in the population is going to have an IQ score between 115 and 125. We're talking here about university level, more or less. Again, that's the area under the curve over here. And you see that the probability, of course, is substantially reduced. We're talking now about 10% of the population, 11% of the population. What is the probability that an individual will have an IQ score larger than 125? We are now really increasing our level over here. This is more or less the IQ score of PhD professionals. And you see that here we are dealing just with 5% of the population, more or less. And finally, just the last example I want to give you is, well, if you want to calculate the probability that a person will have an IQ score of 160 or larger, you cannot even put it here in the graph. Here you have 140, 160 will be over here. And you see that the normal distribution really goes to zero fast in this area. Well, that probability is extremely small. You have the value here, but we are talking here about very special people. We're talking about people like Stephen Hawking, Harry Gasparov, Albert Einstein, Judith Polgar. These are individuals that happens once in a while. Probably we have never met somebody as clever as that. But as we have said, the normal distribution is a very nice mathematical model. It has all these kind of nice properties, mathematical properties. But if that were the only thing, then of course it will not be so relevant in our domain. The important point is that together with all these mathematical properties, the normal distribution seems to happen frequently in nature. And I will give you a couple of examples. These are now real data. This is not a thought experiment or something. This one, for instance, was published in 2006 in the Prevention Chronic Diseases Journal. And there we have the BMI. The BMI is an indicator created by a Belgian statistician, Adolf Keletelek. Is just your weight in kilograms divided by your size in meters squared. It's a single number, but that has a lot of predictive power regarding your general health status. And this was a large study. They included about 1,500 individuals. The average BMI they found there was 25, and the standard deviation was around 4.88. 25 is a little bit high. The normal BMI should be between 20 and 25. Larger than 25 is overweight. But here you have the histogram with a normal distribution overimposed on it. And you can see that it's a quite nice fit. So as an approximation, BMI seems to follow this bell shape, this structure that the normal distribution has. Here you have another example. Now we are talking about birth weights. So this is the birth weight of about 3,000 babies. The study was published in the British Medical Journal in 2002. The average was about 3.4 kilos with a standard deviation of 0.55. And here again, you have the histogram with the normal distribution on it. And you see again that birth weight seems to follow the pattern of the normal distribution. So it's a pattern that comes that pops up in nature very frequently. And that, together with the nice mathematical properties, have made the normal distribution a very useful model in science. And we are going, as I said already before, we are going to get some heuristic understanding of why that is the case, why it's so prevalent, why the normal distribution seems to come out of nature so frequently. Now, the main topic of a statistical inference, of course, is to make inferences about a population. So you want to make quantitative statements about the characteristic of a population. The problem is that populations are typically large. If, for instance, if you want to answer the scientific questions, do men and women earn the same for the same job? That's a very relevant question. Because if the answer is no, then we may have a structural problem in our society, and we will want to correct it. But the problem to assess that question is that we are talking about millions of people. If you take Belgium, for instance, it's not such a big country. You have millions of working men and women. So if you really want to answer the question, you will have, in principle, to just gather information about all these millions of individuals, which is practically impossible. It can be possible, you can make some kind of census. It's going to be extremely expensive, and it's also necessary. So what you typically do, and sometimes it's literally impossible to evaluate all individuals in the population, what you typically do is that you select a random sample out of this population. Let's say you consider 500 women and 500 men, and you gather information about these 1,000 individuals. And then the question is, can I say something about millions with information about 1,000? And that's the whole goal of a statistical inference. So yes, the answer is actually yes, you can do that, but of course you have to follow certain principles, and these are the principles that a statistical inference studies. Now, in statistics, you have different school of thoughts. So statistical inference tries to give us principles to learn from data. So if you gather information and you get data, how can I learn from it? How can I extract value from it? How can I identify patterns in the data? And there are four main schools of thought in statistics. You have the Bayesian paradigm, you have the frequentist paradigm, you have the likelihood paradigm, and you have the information theoretic paradigm. And there has been, if you want, an endless debate in statistics between these different schools of thoughts. You have the Bayesian paradigm that has become extremely popular in recent years due to a number of developments in computational statistics, etc. You have probably the largest paradigms, which is the frequentist paradigm. Then you have the likelihood school, and you have the information theoretic school. And these schools will debate endless about what is the most appropriate way to approach data analysis. What is the best philosophical framework to approach data analysis? If you want my personal opinion, I think that reality is extremely complex, and that we need to have different tools in our toolbox. There may be situations in which the Bayesian framework may be extremely useful. Maybe other situations in which you may prefer to go with the information theoretic approach. Like, for instance, when you're talking about model building, I have a preference for the information theoretic approach. In other situations, you may want to go in the frequentist direction, etc. This course is going to be mostly framed in the frequentist approach, and the frequentist approach is based on the frequentist interpretation of probability. How frequentist thinks about statistics? They say, well, we are going to develop methods to extract value from data, to make inferences based on data. Now, how we assess the validity of these methods, how we can say that these methods are good or bad. Frequentists look at it in the following way. When they see an experiment, the results of an experiment, they think that this experiment is one realization conceptually It is a realization of if you want, an infinity sequence of possible experiments. So they consider, if I repeat my experiment again and again and again, and I apply this method, this procedure, this methodology repeatedly in all these experiments, I want this methodology to give good results most of the time. And if my methodology does that, then it's a good methodology. So they intend to assess the validity of the method by seeing how it works if it is repeatedly used to analyze the outcomes of the experiment. So that is the Frequentis framework. And in the Frequentis framework, parameters are considered unknown constants. They are unknown, but they are fixed. They are not random variables. In the Bayesian paradigms, for instance, they consider parameters as random variables. Or there is a subtle difference there. They quantify the uncertainty about the parameters using a probability distribution. But Frequentis, they follow a different path. Parameters are just unknown constants. Now, let's try to make this a little bit more concrete. Suppose that you have an outcome, a response variable. We are going to call it y, and we are going to use the same notation for the random variable and for the realized variable. So value. Sometimes you have in the literature that they use, for instance, a capital letter to denote the random variable, and when you observe a value, they use a small letter. We are going to use the same symbol just to simplify a little bit the notation. And consider that you collect that outcome on n individuals. You have n random variables. You have a sample of n individuals. And we're going to gather all this information in one n-dimensional vector. We call this vector y, but bold. We're going to use the bold font for vectors and matrices. And then for scalars, we're going to use just the normal letters. So here we have our data. Now we are going to assume that each of these random variables have a distribution, a common distribution or density that we are going to call P of y theta. So we are going to assume that each of these random variables has been generated by a common latent data generating mechanism. Now, what is producing an outcome in an experiment? If you are thinking about IQ score, what is the underlying process that is generating these scores when we see them, when we observe them, may be an extremely complicated process. It may be a very complicated process taking place in the brain of these children, like we saw at the beginning. But we are going to assume that that complicated process can be modeled, described using a probabilistic model. Now, that in itself is an assumption. It doesn't have to be like that. Sometimes processes are deterministic. There is no randomness in that. You don't need a random model to describe gravity. It's a deterministic process. But we have learned, and this is some kind of an heuristic statement, we have learned that many processes, especially complicated, complex processes, can be very well described by a probabilistic model. So we are going to assume that each of these outcomes we are observing in our samples is emanating from an underlying probabilistic model. And for the moment, we are going to assume that this underlying probabilistic model contains only one parameter, theta. So the dimension of theta is going to be 1. Later, we're going to generalize that. Now, we're going to keep making assumptions. We are going to assume that all these outcomes are independent. They are realization from the same underlying probabilistic model, and they are independent. Independent means that the outcome we observe in one subject has nothing to do with the outcome we observe in another subject. So if I observe the IQ score of one child, I'm not going to learn anything about the IQ score of another child, because these are independent realizations. And under that set of assumptions, then the probability of observing this data set over here, that probability can be written in this way. That probability is just the product of the probability of the individual outcomes. And typically, you formulate your scientific question, whatever that scientific question is, in terms of the parameter theta. So typically, the question you want to answer is just formulated in terms of this theta. So the purpose of a statistical inference is to draw inferences about this unknown parameter theta that govern this underlying probabilistic process that generates the data. That's typically what we want to do. Now, the first thing you want to do is I want to guess the value of theta, right? Was theta equal to 2, 3, 4? What is the value? So we want to make a guess of this unknown parameter. And we call that point estimation. And of course, the only thing you have in your hands to guess the value of theta is your data. So you want to use your data to make a guess of this parameter. And you want this guess to be good. Now, the question is, what do you mean by good? Well, we are going to discuss that shortly. So we are going to call that guess theta of y. By the way, for some strange reason, in my computer it is okay, but when you upload this presentation in Collaborate, it gets transformed, and for some strange reason the head gets, this is very annoying, the head get out of the theta. So typically we should have this head over here in the following way, but I mean, nothing to do, is something with Collaborate. It should be like this. Now this guess is going to be a function of y. You are going to, it's just a formula. We're going to use the data to guess the unknown value of theta. And of course, if you repeat your experiment, and your data will change because your data have sampling variability, there's biological variability. When you repeat your experiment and you get different data, then your guess is going to change. You're not going to make exactly the same guess every time. There will be some variability depending on the variability in y, depending on the variability in the data. So your guess, your theta head, is in itself a random variable, and the distribution of your theta head is going to depend on the distribution of y. Now the question is, when I'm going to say that this guess is good, when I'm going to say that this procedure, this formula of the data that I'm using to guess theta, is a good procedure. And Frequentis, Bayesians may have a different point of view, but Frequentis look at it as well. I want this estimator, we call theta head estimator, I want this estimator to concentrate around the true value I'm trying to estimate. So suppose that you have here the true value you're trying to estimate. Here is your theta, and you have your estimate, which is your estimator, which is theta head over here. So if you repeat your experiment again and again and again, you're going to get different guesses. Sometimes you will be over here, you will overshoot it a little bit. Sometimes it will be over here, you will undershoot it a little bit. There will be variability in your estimates. And Frequentis they say, well, it's going to be a good estimate. This estimator, the estimate is the observed value. The estimator is the procedure, it's the function of the data. I'm going to say that this is a good estimator if it generates values that are concentrated close around the true value. I may do it a little bit over or a little bit under, but in general, I'm going to be close to the true value. That's the Frequentis mindset. If you repeat the experiment, I'm going to stay close to the true. I may have some variability depending on the data I'm getting, but I'm going to stay close to the true. If I manage to create such an estimator, I will be happy. Now, how you measure closeness? Because it's a random variable, right? Well, statisticians have defined what they call the mean square error, MSE, a mean square error of your estimator. And what is the mean square error of your estimator? It is the average distance between your estimator and the true value. So what you have here is the distance between the estimator and the true value. So let's see this again. You have here the theta, the true value over here, and you have a realization of your estimator. There is a distance between the true and your estimate. And this distance is given over here. And then the mean square error is just the average distance. Remember that this theta y over here, theta head y over here, is just a random variable. So what you're going to do now is you're going to calculate the average distance between the true value and your estimator. And you want that average distance to be small. Sometimes you may have an experiment where you get very far from the true, your estimate goes very far to the right or very far to the left. It can happen, but as an average, and this is the average taken with respect to the distribution of y. Why? Because theta head is a function of y over here, but as an average, you want your estimator to be close to the true. So the mean square error is just the average distance between your estimator and the true value you're trying to estimate. And it's as an average that distance is small, then you will say you have a good estimator. Now you can do a little bit of math, and you can see that this average distance can actually be decomposed. the mean square error, can be decomposed into two different factors. One is just the variance of your estimator, the variability of your estimator. The other one, the one over here, is a little bit more interesting. If you want, we call it the bias of the estimator. Now, what is the bias of an estimator? The bias of an estimator is the average value of your estimator minus the true. That's it. It's the average value of the estimator minus the true value you're trying to estimate. And we will say that an estimator is unbiased if the bias is zero. So essentially, theta hat is unbiased if the expected value of theta hat, equals the true value you're trying to estimate. Expected value of theta hat equals theta. In that case, you're going to say that the estimator is unbiased. From an intuitive point of view, what that means? Well, that means that if you have your true value over here, and you repeat your experiment again and again and again, you're going to get guesses that move around the true value. They fluctuate around the true value. A bias estimator doesn't follow this property. So in the bias estimator, you may have the true value over here, and if you repeat the experiment again and again and again, your estimator may be moving around something else, like here. So your estimator may be getting values that move around some other value, not the true value. That will be bias estimator, that would be an unbiased estimator. Now you may think, well, unbiasedness is a nice property. However, we will see that there are many bias estimators that are very useful. You may even have a bias estimator that is better than an unbiased estimator. Actually, unbiased estimators do not exist all the time, and sometimes they can be meaningless. So it's a nice property, but it's not like like we only want to look at this type of estimator. I will give you an example. Suppose that you have, again, a random variable yi. They are observed on n individuals, and the variables are ID, independent, identically distributed. And suppose you want which distribution, it doesn't matter. But suppose you want to estimate the mean, the average in the population, and you want to estimate the variance in the population. And we know the classical estimators for that, right? We know them from high school. You use just the sample mean and you use the sample variance. Now, the sample mean is unbiased. The sample mean, the expected value of the sample mean is the mean in the population. So if you repeat your study again and again and again, your sample mean is going to fluctuate around the population mean. But the sample variance is biased. You can see here that the expected value of S squared is not sigma squared, the parameter you're trying to estimate, is smaller than sigma squared. So if you have sigma squared here, over here, the sample variance is not going to fluctuate around the sigma squared. It's going to fluctuate around something else that is smaller than sigma squared. Actually, this value over here. Now, the sample variance is asymptotically unbiased. And what we mean by that is that if n is large enough, this term over here will go to 1. So that means that it will be fluctuating around a value that is not sigma squared, but is extremely close to sigma squared. And for all practical purposes, that will be the same. So it's asymptotically unbiased, but it's a bias estimator. Now, what is the importance of unbiasedness as a concept? That all else being equal, an unbiased estimator, of course, will be preferable. However, in practice, all else is not equal. Unbiased estimators are often very useful. So it's a nice property. We will frequently want to have it, but is a debatable property to a certain degree, because you may have a bias estimator that have a smaller mean square error. That means essentially that it will its values will be more concentrated around the true, even though they are biased, than certain unbiased estimators. So it's something you need to take with care. Let me give you an example. A situation where unbiased estimators may be weird. Suppose that you want to model the number of meteorites greater than 1 meter diameter that strike Earth in a year. That may be an important thing to know. I mean, 1 meter may not be a big issue, but if you have a meteorite larger than 50 meters, you can get into trouble if it strikes against a town or against a city. So you want to calculate the probability that you will have 1 or 2 or 3 meteorites with this characteristic hitting Earth every year. Suppose that you want to model the number of patients arriving in an emergency room between 10 and 11 p.m., a Saturday between 10 and 11 p.m. in certain hospital in Hustle. That's also a very important thing to model because you need to organize your staff depending on how many patients you're expecting in such an eye. Suppose that you want to model the number of incoming calls at the telephone switchboard per minute. When you're dealing with this kind of phenomena, counting process, the number of events that happen in certain time window or in certain region of space, you typically will use something called the Poisson distribution that you have it over here. So y is just a natural number, is the number of events, can be 0, 1, 2 until infinity. And here you have the probability that you will observe that amount of events. And that probability is the Poisson distribution. It's lambda to the power y, e to the power minus lambda divided by the factorial of y, where the factorial of y is the product of all natural numbers from 1 until y. Now, the Poisson distribution, we will later in the course study the Poisson regression model. It's a very important distribution. The Poisson distribution has a characteristic, and it is that the expected value is equal to the variance. The mean is equal to the variance, in contrast to the normal distribution, because for the normal distribution, the mean and the variance are independent. And that's a very special thing of the normal, that the mean and the variance are governed by two independent parameters. In generalized linear models, that's not the case most of the time. Most of the time, the mean and the variance are related. And in the Poisson model, in the Poisson distribution, they are exactly the same. And that is a problem. We see later on that in practice, that becomes frequently a problem, and we will learn some methods to try to solve this problem later on in the course. Now, suppose that you have a Poisson distribution and you want to estimate the probability of not observing any event square. You want to estimate the square of that probability. That's e to the power 2 times minus 2 times lambda. And you have data, you have one data point, you have sample size 1, and you want to estimate this parameter over here. And you may say, well, what a strange thing to estimate. Why should I want to do that? Well, it's not that strange. Suppose that you are dealing with incoming calls per minute at the telephone switchboard. Or you may be, this telephone switchboard may sound like a very old thing, but suppose that you are just modeling the number of times a web page get hit, people want to open it in 1 minute. Whatever, we're going to use the telephone switchboard. And how many calls you're going to get in 1 minute can be modeled by a Poisson process with lambda denoting, of course, the average and also the variance of this distribution. Now, this parameter we are trying to estimate here, this theta, then will be the probability that you get no calls in the next 2 minutes. So suppose that you're dealing with these problems, that for instance, that nobody will try to enter the web page in the next 2 minutes. So suppose that you want to estimate that probability. What is the probability that in the next 2 minutes, I will get no calls? Nobody will try to hit the web page, right? And we have information about 1 minute. And this minute, so many people call, or so many people try to open the web page. That's the data I have. And now, using that data, again, we want to estimate the probability that in the next 2 minutes, nobody will call. Well, you can show mathematically that the only unbiased estimator for this parameter theta over here is given here below. It's -1 to the power y, where y is your data, is the amount of people that call in the present minute or in the past minute. And you can see that this is the only unbiased estimator, but you can see that it's kind of a weird thing, because if 100 people call, if this is the data you have, then the probability that nobody will call in the next 2 minutes will be equal to 1. So you can go home in the next 2 minutes, you can go to the toilet, whatever. You're certain that it will not happen, which is kind of a weird thing. But can be even more weird. If your data is that you have gotten 101 calls, then you will get a probability of -1, which simply doesn't make any sense. So unbiased estimators may have kind of weird characteristics sometimes. And I'm just saying this, they are nice estimators. This is a nice property, but is, like we said before, can be debatable, whether you just need to go for a unbiased all the time. So here we have Frequente said, well, if I'm going to make a guess, I'm going to make a point estimate. We call that a point estimate. It's just one guess. If I'm going to make a guess, then I use something called an estimator, which is essentially a function of the data, and the data random. So my estimator itself will be random. So when I'm going to say that I have a good estimator, well, one possibility is to say, well, I want my estimator to be unbiased. I want my estimator to fluctuate around the true value. When I repeat my experiment, I want that to happen. That's the unbiasedness property. And that may be something you may want to consider to say if your estimator is good or not. Another property is called consistency. And what is the consistency? When we say that an estimator is consistent, and this is a much less debatable property. I think that everybody wants their estimator to be consistent. What is that? Well, here you have the mathematical definition. The mathematical definition is take a value epsilon, which is positive. Which value? You choose it. Doesn't matter. 0.00001. Take it as small as you want. My estimator is going to be consistent. If when my sample size increases to infinitive, the probability that my estimator will be far away from the 2 by an amount larger than epsilon, that probability becomes 0. So essentially, that means, or if you want, you can write this in another way, the probability that this expression, this distance, the probability that this distance is smaller than epsilon, that will go to 1. So essentially, what consistency says is that if you have enough information, you can get as precise as you want with respect to the truth. If you have enough information, you can get as close to the truth as you want. So the more data you gather, the more precise your conclusions are going to be. You're going to get as close to the truth as you want. You may need a lot of data, but your estimator has this property, and that's called consistency. And for instance, a very well-known consistent estimator is the sample mean. Actually, we have a special name for that in probability. We call it the law of the large numbers. That means that if you gather enough information, your sample mean is going to go so close, as close to the true mean as you want. So you will be able to assess, to estimate the true unknown mean in the population with whatever level of precision you want. You just need to have enough information. And that's the so-called law of this large number. The sample mean is a consistent estimator. Now, what is the relationship between consistency and unbiasedness? Because we have seen that what we are doing now is we are trying to formulate properties we want our guests to satisfy. We're formulating properties I would like my estimators to satisfy. But we have seen two, unbiasedness and consistency. What is the relationship between these two things? Are unbiased estimator always consistent? Are consistent estimator always unbiased? Or these are kind of independent properties? And they are kind of independent. So here you have an example of an unbiased but not consistent estimator. Suppose that you have your data, again, your yi's, right? From y equal y1, y2, etc. And you're going to construct an estimator T for the mean of the data in the following way. You want to estimate the mean in the population. And we're going to construct an estimator that chooses just only the first value. So we are going to estimate mu using only y1. And you will say, well, that's a very stupid choice because you're throwing away all the other values. Okay, fine, but it's just to show, it's to make a theoretical point. Now, that estimator will be unbiased. If you always take the first observation in your data, it will fluctuate around the true value because all these data are IID. So they are emanating from the same underlying distribution, so it is going to be unbiased. But obviously, it's not going to be consistent. Doesn't matter how much data you gather if you just select the first one and you throw away all the rest. You're not going to get closer to the true value of mu in any way. So an estimator can be unbiased, but not consistent. And you can have the opposite. Can be biased but consistent. And a very nice example of that is the sample variance, S squared. We saw that it's biased. Is actually negatively biased. It fluctuates around a value that is smaller than the population variance, but it's consistent. If you increase your sample size, you will get as close as you want to the population variance. Now, the sample variance is asymptotically unbiased. You can say, well, but you're kind of not playing fair here because it's true it's biased, but if I increase the sample size, the bias goes to 0. Fair enough. However, you can construct a consistent estimator that is biased, and the bias does not go to 0 with n. So you have consistent estimators that are biased, and this bias doesn't go to 0 with n. So they stay biased no matter how large n is, and still they are consistent. That's possible. So these are two properties that are kind of independent. You can have a bias, an estimator that is consistent. You may have a consistent estimator that is biased. They are kind of independent properties. Now, one of the characteristics we try to study frequently is the mean in a population. We really learned about the average behavior. So we say, as an average, treatment A is better than treatment B. As an average, men earned more than women. As an average, so we, in many situations, we formulate our scientific questions in terms of means, in terms of average. And therefore, I mean, we know that the best guess we have for the population mean is the sample mean. And therefore, it will be very useful. We know it's consistent. We know it's unbiased. So the sample mean satisfies already the two properties we have defined until now. But is there something else special about the sample mean? And to get insight into this, what we are going to do now is some kind of a simulation study. We are going to consider the following situation. We are going to generate data emanating from 4 different populations. You are going to study data that come from a normal population, a gamma population, a uniform population, and a beta population. And you can see that these 3 over here, the normal number, the gamma, the uniform, and the beta, they are rather non-normal. They are skewed, they are rather non-normal. And we are going to do the following experiment. Nowadays, our computers have become so powerful that you can do this easily with a laptop. We will go to the normal population first. So we come here, and we will select a sample, a random sample of 4 observations. And we will calculate the average. So we have the first average. The first average from a normal population first on 4 individuals. And we will come back and we will select another 4 observations, and we will calculate another average, and we will denote that by x bar 2. And we will repeat these steps 20,000 times. So we will end up with 20,000 sample means based on 4 observations here in the normal population. But we are going to repeat the same processes for the gamma population and for the uniform population and for the beta population. So essentially, we are going to have 20,000 sample means based on 4 observations in the normal population, in the gamma population, in the uniform, and in the beta. And once we have these 20,000 sample means, we can construct a histogram of them. And when you do that, this is what you get. Now, this is pretty interesting, because the data are not normal, at least in these 3 cases, are clearly not normal. However, the sample means, based on 4 observations, the sample means emanating from this non-normal data seems to be quite normal if you look at it. Okay, that's interesting, but I just had a sample of 4. What if I increase my sample size? What if I consider a sample of 9 and I repeat the same simulation, but now considering a sample means based on a sample of 9 individuals? Then you get this. And this is even more interesting. This is more normal. So sample means of 9 individuals, sample means of an outcome of 9 individuals, that this outcome is clearly not normal. The sample means seems to follow the normal pattern. And if you base your sample means not in 9, but for instance in 25 observations, then they are clearly normal. So this is one of the most important results in statistics probability theory, but I would say even in science. And it's not just in this simulation, you can prove this mathematically. And it's such an important result that we call it the central limit theorem. So essentially, sample means follow a normal model when the sample means are based on a large sample size. And this is called the central limit theorem. So you have the univariate version and the multivariate version, and we're going to see both of them. So let's start by the univariate version. So suppose that you have data. You have a sample of n individuals, and these outcomes are now univariate. They are not vector, they are just numbers. And these random variables are coming from certain underlying distribution that we don't know what it is, but it has mean mu and variance sigma square. So whatever mechanism is generating these outcomes, whatever distribution is generating these outcomes, it has a finite mean and variance. But it can be whatever. It can be a uniform, it can be beta, it can be gamma, you name it. And now we are going to construct this variable, the root square of n times the sample mean minus mu. And you can prove mathematically that when your sample size increases, this new random variable follows a normal distribution with mean zero and variance sigma square, approximately. The larger your sample size, the better the approximation. And that's what we call the central limit theorem. So the root square of n times the sample mean minus mu follows, if n is large enough, if n goes to infinity, it follows a normal distribution with mean zero and variance sigma square. Or if you want, the sample mean follows a normal distribution with the same mean as the original data, mu, and the variability, which is the variability of the original data, sigma square divided by n. And that happens approximately if n goes to infinity. That's called the central limit theorem. What about the multivariate case? It's exactly the same. The only difference is that now the outcomes are vectors. So now you have a vector for individual 1, a vector for individual 2, and so on. And these vectors are again IID. They are independent and identically distributed. So there is a latent stochastic process, probabilistic model generating these outcomes. And this probabilistic process can be whatever you want, but it needs to have a finite mean and a finite variance covariance matrix. Now we are dealing with vectors. We don't have a variance. We have a variance covariance matrix. And we are going to construct the same type of random variable, root square of n, then the sample mean minus the mean in the population. So the sample mean now is the mean of each coordinate of this vector. The sample mean of each coordinate. It's the vector containing the sample means of each coordinate. And you can show that if n is large enough, then the distribution of this new random variable over here, root square of n, the sample mean minus mu, gets closer and closer to a normal distribution with mean zero and variance sigma square. And this is a result we are going to use very frequently. It's one of the fundamental results in probability. We call it the central limit theorem. And you remember the discussion at the beginning of the lecture about the prevalence of the normal distribution in nature? We were asking ourselves why it pumps up so frequently in nature. Well, the central limit theorem may help us to answer that. Suppose that you are studying, for instance, body length. Now, your body length, your size, is the result of so many factors. There may be a racial component. There may be genetics component. There may be factors related to the type of food you eat or you ate when you were a child. It may be the economical component. There may be so many factors playing a role to produce your size. And you may at least think heuristically that your size is the result of the average effect of all these factors. And we know that averages tend to be distributed in a normal way. And so if the number of factors is large enough, then the average may be close to a normal distribution. And this is not a mathematical proof, but it's an heuristic argument that may explain why we see the normal distribution so frequently in nature. Now, another important result related to this is the so-called delta method. And the delta method is something we're going to use a lot later on to construct approximate tests, confidence intervals, estimators of variance, etc. Now, what the delta method says, suppose that you have a sequence of random vectors. So you have here a vector yn, which has p components. So you have a p coordinates. This is the first component for your vector, the second component, etc. And here you have the p component of your vector. You have a sequence. You have that vector measured several times. We use here this t, that means the transpose of a vector. So vectors typically are represented as columns, and if you transpose them, then you get a row. So that's the only meaning of that. Now, suppose that the random vectors, they have certain mean, mu, that doesn't depend on n, and suppose that when these random vectors, when the sample size increases, this new random variable, the root square of n, yn minus mu, this new random variable tends to the distribution of another random variable set. So set has a distribution, and we have this random vector, and when n is large enough, this root square of n, yn minus mu, that start getting closer to the distribution of that new vector gets closer to the distribution of set. This is very general because set in principle can have whatever distribution you want. And suppose that you want to transform your data. So you don't want to work with y, you want to work with psi of y. This is a transformation of your data. And why you want to transform your data, there are many reasons for that. You may want to change the units of measurements. You will want to, whatever it is. And this transformation, of course, is now a transformation that goes from a p-dimensional space, Rp, to a k-dimensional space, Rk. So because you take your vector yn that has p dimension, and you transform it into a new vector, psi1 of y, etc., psi k of y, a vector that have k dimensions. So you go from a p-dimensional space to a k-dimensional space. Now, such a transformation, such a function, such a map has something associated with it that we call the Jacobian of the transformation. What is the Jacobian? Is the derivative of your function psi with respect to y. So that's a matrix. In the position ij of the matrix, what you have is the derivative of the I component of psi divided by with respect to the j component of y. So for instance, you calculate the derivative of psi here with respect to y1, here we go, y1 is difficult to write with this, and then you're just calculating the derivative of each component with respect to y1, and that will give you a row of the matrix. So you don't need to understand all the mathematical details, but it's useful to have some understanding of what is going on, and we call that the Jacobian of the transformation. Now, suppose that you're interested now in the distribution of the transformed data. You know that the original data, this new vector here, root square of n times yn minus mu, the distribution of that quantity gets closer and closer to the distribution of Z, whatever the distribution of Z is. But now I transform my data, and I'm going to construct the same type of variable, root square of n, then y at n minus psi of n minus psi of mu. When n increases, what happens with the distribution of this? Well, it gets closer and closer to the distribution of a new random variable here. Which random variable? The original data got close to the distribution of Z. So the transformed data over here gets closer to the distribution of a new random variable, which is the Jacobian of the transformation, evaluated in the mean, times Z. And this is the most general expression for the delta method. I know all this looks rather mathematical and abstract, as again, I don't pretend that you understand every little mathematical details, but just conceptually what is going on. And I will give you an example that is used very much. Suppose that this set here, suppose that this set over here follows actually a normal distribution. So what we are saying is that the root square of n, yn minus mu, that gets close to a multivariate normal distribution with mean zero and variance covariance matrix Z. So asymptotically, yn follows a normal distribution. And suppose that I transform my data using certain map, certain function psi. What is now the distribution of psi of n? Well, asymptotically, we construct now this random variable, root square of n, psi of n minus psi of mu, and you can show that this new random variable over here will follow then a normal distribution with mean zero and this variance covariance matrix. And this is a result in the delta method that we will use very frequently. Okay, let's see this with an example. We are going to now focus on one specific type of distribution. It's called the Bernoulli distribution. It's named after the Swiss mathematician Jacob Bernoulli, and is a discrete probability distribution of a random variable that can take only two values, 0 and 1. So the variable takes value 1. Typically 1 represents success, a value 1 with probability pi, and a value 0 with probability 1 minus pi. And the probability distribution of such a random variable is given here. It's pi to the power k times 1 minus pi to the power 1 minus k. So if k is equal to 0, you get this vanish, and you get here 1 minus pi. And if k is equal to 1, then this vanish, and you get this over here vanish, and you get pi. So that's a very simple distribution. You can show the expected value, the average, the mean of y is pi, and the variance is pi times 1 minus pi. That's the Bernoulli distribution. You all probably know about it. Now, suppose that you have a sample of Bernoulli distributions, and each observation, the observations are independent. So you have n trials. It's like when you toss a coin 1,000 times. Each individual outcome is a Bernoulli. It's head of 1 or 0, head or not head. And suppose that you have a sample they are independent, and you want now to quantify the number of successes. Or you have a treatment and you apply it to n individuals, and 1 is cured, 0 is not cured. If I apply my treatment to 100 individuals, what is the probability that 50 of them will get cured, 60 of them will get cured? The number of successes in a trial. And this is essentially the sum of all the Bernoulli all the Bernoulli outcomes, right? If you consider the success is 1, and that's just, you can always consider that, then the number of successes in a trial is the sum of this individual Bernoulli's outcome. And that follows something called the binomial distribution, which is given by this expression over here. So here you have the combinatorial terms, is the combinations of n and k. The ones of you that don't know what is that, please Google it. And this is just the probability that you will observe k successes in n trials. And this is again a probabilistic model, it's a probability distribution, a probability function, and this random variable, this binomial distribution, both the Bernoulli and the binomial distribution are going to play a very important role later in the course, because this is the underlying mechanism behind logistic regression. So the binomial random variable has a mean that is equal to n times pi, and then a variance which is n times pi 1 minus pi. But it's essentially a sum of Bernoulli's random variables, and we know because of the central limit theorem that sums of independent random variables tends to be normally distributed, right? The average is the sum divided by n. The average is normal, and therefore the sum tends to follow also a normal distribution. Is some kind of basic math. So why the binomial new random variable, which is the sum of independent Bernoullis, the central limit theorem guarantees that it will be approximately normal with mean n times pi and variance n times pi 1 minus pi. And this is actually the case. We can see this in another simulation study. So suppose that you have n repetitions in your experiment. You have a sample of n individuals. Each of them produces a Bernoulli outcome with a probability of success equal to 40%. And you want to, you know that the number of successes in this sample, the number of successes in repetitions will follow a binomial distribution. And the central limit theorem guarantees that this, the number of successes in 100 repetitions is going to be approximately normal with mean 40, 100 times 0.4, and a variance equal to 24. And here we just have a small R code to generate data and to assess this. And indeed, here you have the probability given by the binomial distribution. So if you consider just the binomial expression we saw here, and you calculate the probability of having 1 success in 100 trials with a success probability of 40%, 2 successes in 100 trials, 3 successes, and so on, using this formula, then you will get this value here. So this is the probability of getting 25 successes over here, the probability of getting, I don't know, 35 successes over here. That was a bad line over there, 25 successes over here, and so on. And as you can see, well, the probability of getting very little success is low. The probability of getting a lot of successes is low. Most of the mass of probability concentrates around 40, between 35 and 45. This is now done with the formula for the binomial distribution. But if you superimpose there a normal distribution, look at it. So essentially, you will get the same result. The approximation is very good. And that's just the result of the central limit theorem. Let's give a concrete example of this. We all know the Titanic story. It was one of these things that events that shocked humanity at the time, and it has a stays in the collective memory of human of our society, of mankind. And the story is that the 10th of April, 1912, the largest passenger steamships in the world left Southampton, England, to go. The idea was to go to New York City. That was the stage of the art at that time of technology. And we were so proud of it that the media at the time, the newspapers were saying that this was really unsinkable. There was no way that this ship could get into problem. However, in the first trip, April 14th, just a few days, 4 days after leaving Southampton, England, 11:40, the ship struck an iceberg. and it sank just a couple of hours later. That was a huge shock at the time. Nature sometimes have its own way to make us humble, and about 1,500 people died in that accident. It was the deadliest peacetime maritime disaster in history. Now, here you have some images of the ship. Even with the standards of today, is really an impressive machine. If you look at it, it was really very impressive. And we have a lot of information about the people that were on the ship that day. We have their names, we have their ages, we have a lot of information about them. Now, let's assume that we consider each individual an observation. And we are going to consider an outcome for each individual, a very simple outcome: survive, yes or no. So it's a Bernoulli outcome. So Y1 is 1 if individual 1 survive, is 0 otherwise. And there is a probability of survival, which is pi, and it's the probability that yi is equal to 1, and there was a probability of dying, which would be 1 minus pi. And we are going to assume that these are independent observations. That's maybe not true, because people may have helped each other, may have increased the probability of survival. They may have fought against each other. An outcome of one patient may not be completely independent of the outcome of the other patient. But essentially, for what we are going to do here, even if they are not independent, it will be fine. And we are not going to work with the probability of surviving, but we are going to work with another thing that we call the odds of survival. And this is another quantity we are going to see later in logistic regression. Now, what is the odds of survival? It's the probability of surviving over here divided by the probability of dying. That's the odds of survival. So the odds of an event is the probability that the event will happen divided by the probability that the event will not happen. That's called the odds. So for instance, if you have an odds of survival equal to 2, that means that for every 2 passengers that survive, 1 dies. So the probability of surviving is 2 times larger than the probability of dying. That's a good thing. If you have an odds of survival of 0.5, that means that for every passenger that survive, 2 die. So the probability of dying is 2 times larger than the probability of surviving. And the term comes from horse racing. That's one odds. So if you say somebody won against all odds, that means that the probability of losing were many times larger than the probability of winning, and still the person won. That is the interpretation of odds. So we are not going to be focusing on the probability of surviving, but in the odds of surviving. Now, if you calculate now the number of people of survive, which is just the sum of all these individual Bernoulli processes, that will follow a binomial distribution with parameters pi and n. So the mean will be n times pi, the variance will be n times pi times 1 minus pi. And the central limit theorem tells us that the average of this quantity over here. So if we divide now by n's, if we calculate y divided by n, notice that this is just the number of survival divided by the total number of passengers. That is an estimator of the probability of surviving, right? So if you take the number of survivals and you divide it by the total sample size, that's an estimator of the probability of surviving, and that's just an average. So the central limit theorem guarantees that asymptotically follows a normal distribution with mean pi and variance pi 1 minus pi divided by n. Just go back to the central limit theorem and do a little bit of math. Now, we can estimate the odds of survival by just plugging in the estimated probability in the expression of the odds. So if you go to the odds and you plug in here now the estimate of the probability, you get an estimate of the odds. And that's what we are doing over here. So that would be our estimator for the odds of surviving. And we know that the estimator of pi follows a normal distribution. So what is the distribution now of the estimator of the odds of survival? And there we can use the delta method we saw before. Because essentially, we are not going to work with the odds of survival, but with the logarithm of the odds of survival. So what I'm doing is I'm transforming pi, my estimator of pi hat, to estimate the log of survival. What I'm doing is the log of survival. This is my new estimator. That is just the logarithm of my estimator of pi divided by 1 minus the estimator of pi, right? That's what we are doing. So as you can see, what we are dealing here is with a function that is like this, g of x. And this function has a derivative. You can show it very easily. That's the derivatives of the function. And now what you have is you can apply the delta method because pi itself, pi hat, follows a normal distribution because of the central limit theorem. And now you can see that the logarithm of the estimator for the odds of survival follows asymptotically a normal distribution, which means the log of the odds of survival, the real parameter, and which variance, this is the variance it follows. So we now, applying the delta method, we can get an estimate of the variance of the estimator for the log of the odds of survival. Now let me tell you something. This is a situation in which non-biased estimator exists. So if you try to find an unbiased estimator of the log of the odds of survival, there is no such an estimator. So they are not unbiased estimator in this case. Now you can do this in R. There is a library called MSN, and this library, well, with this library you can get the data set, the Titanic data set. So here you have the data. This is individual one that survived, was in first class, was I think a female, and was 29 years old. So now if you calculate the mean of the survived variable, then you get an estimate for the probability of survival, right? This is what we are doing over here. And then if you calculate the logarithm of that probability divided by 1 minus that probability, what you're getting here is an estimator for the log of survival. This is what you have here. And then the sample size is the number of arrows in the data. And the variance for the probability of surviving is given here. Well, here you have the expression, right? This is the one we saw before, is the probability of surviving times 1 minus the probability divided by n. And then there is a function in R called the delta method. And you can apply that function to calculate the standard deviation of the estimator of the logarithm of odds of survival. The only thing you need to do, you need to pass your g function over here, you need to pass the probability of surviving, and you need to pass the variance of that probability. And once you do that, here you get the values that you need. So this is the standard deviation of the odds of survival. The standard deviation, sorry, not because we squared it, that's the variance. So that will be an estimator for the variance of the log of survival. Sorry, this is the variance of the estimator for the odds of survival. Now the logarithm is already back transformed over there. So fine, we have done the following. We have considered that we have a sample, that this sample has emanated from an underlying probabilistic stochastic model, an underlying model that has certain parameter theta. And what we have done is, well, basically we want to study we want to make inferences about this parameter theta. Why? Because typically you formulate your scientific question in terms of theta. So we are making a couple of assumptions here. We are assuming that there is an underlying common generating mechanism that is producing the outcomes we see in our sample. And this underlying generating mechanism is probabilistic and depends on certain parameter. And we are interested in that parameter because our scientific questions can be formulated in terms of that parameter. And the first question we were trying to answer is, well, can I estimate that parameter? Can I use my data to make a good guess of that parameter? And we call that procedure point estimation. And what we are going to see, what we have said, well, you need to construct something called an estimator, which is just a formula of the data. It's a function of the data, and therefore is itself random. And okay, when I'm going to see that that guess is good, when I'm going to say that this estimator is good, and we have considered different properties. Well, one possibility is I want an estimator that minimizes the average distance between my estimator and the true value, the realization of my estimator and the true value. Because if I repeat my study again and again and again, and why you are doing that? Because we are in the frequentist mind frame. So if I repeat my study again and again and again, I'm going to get different guesses. And what I want to do is I want that as an average, the distance between my guesses and the true should be small. So I want to minimize the mean square error. So the average distance between the estimator and the true should be small. If I can achieve that, I'm going to be happy with my estimator. But then we did a little bit of math and we realized that the mean square error can be decomposed into two factors. One is the variability of the estimator, none. The other one is something called the bias, which is the difference, the square difference between the average value for the estimator and the true value I'm trying to estimate. And if that component is zero, we call the estimator unbiased. And why this is nice? Well, intuitively speaking, if an estimator is unbiased and you repeat your study again and again and again, what you get is that the values you're going to get are going to fluctuate around the true. And that looks like a reasonable, nice property to have. However, intuition may be misleading. And we have seen that sometimes unbiased estimators do not exist. Sometimes they exist, but they are kind of nonsensical, like this Poisson case we saw. Sometimes you have estimators that are biased, but are still very useful, like the sample variance, etc. So unbiased estimators are a nice category we would like to take into account, but we would like to look a little bit further as well. Sometimes biased estimators may, for instance, have a smaller mean square error. So as an average, they are closer to the true than the unbiased estimator. That can happen. So that's what we did regarding unbiased, but we then propose a second property, which is called consistency. And I think this is a less debatable property because consistency essentially says that if my estimator is consistent, what that means? That means that if I have data enough, I can get as close to the true as I want. And that's a very good property. It tells me that I really can get as precise as I want. I just need enough information. So when the sample size increases, the probability that I will be further away from the truth, that certain value, whatever value you choose, that probability will go to zero. So you would get as close as you want. And that was called consistency. And then we studied a specific case, which is the sample mean. And why we went into that specific case? Because in many situations in science, we are interested in the average in the population. And the sample mean satisfies both conditions. It's consistent and is unbiased. Consistency, in the case of the sample means, receive a very special name. It's called the law of the large numbers. But the sample means satisfies still another very nice property, which is asymptotically normal. And that's a result of the central limit theorem. And it means that if you have a sample, and this sample may be coming, these observations may be coming from a population that is not normal at all, but this underlying probabilistic process that is generating the data has a finite mean and a finite variance. It's just everything you need. If you have that, then if your sample size is large enough, then your sample means will tend to go, or the distribution of your sample mean will be close to a normal distribution. So sample means comes from a normal world, even though the observations you use to construct the sample means may be non-normal at all. Now, the problem with all these things we have been doing until now is that we're making one single guess. And okay, you calculate a sample mean and it is 10.35, right? Okay, but if I repeat my study, I'm not going to get that value 10.35 again. I'm going to get something different. How much different? Well, I don't know. I mean, for this study, it was 10.35. So you would like to quantify the uncertainty. You can calculate a standard deviation, but when you want to quantify uncertainty, a very useful tool is probability. So to make probabilistic statement. And what we are going to do now is we are not going to make just one single guess. We are going to guess with an interval. We are going to give a range of values for these unknown parameters. And we are going to call that a confidence interval. And we're going to make a probabilistic statement about that interval. So essentially, again, you have data, we have observations yi, and we are going to assume again that all these observations are emanating from an underlying common probabilistic model that we call P of yi, and its model depends on a parameter that I'm going to call theta. And if the observations are independent, then the probability of the data, the probability of the experiment, of the whole vector of observation, can be written as the product of the individual, the probability of the individual outcomes over here. And we want to estimate theta. We are not going to do that anymore with a point estimate, but we are going to construct an interval based on the data. So the interval, again, is random, because if I repeat my experiment, I will get different data and I will get a different interval. right? It's like the point estimate. The interval itself will be random. But now I will make probabilistic statement. That's the difference with the point estimate. So you can think about a confidence interval as an algorithm. You give me input and I give you output. You give me data, I give you an interval. You give me more data, another data set, I give you another interval, and so forth. Now, I'm going to construct these intervals, these stochastic intervals, in a smart way. And what I mean by smart is that the probability that the true value of theta will lie in that stochastic interval, that probability is going to be 1 minus alpha, and alpha is a parameter I'm going to specify myself. And that's the way I'm going to construct these intervals. So frequently in applications, you consider alpha equal to 0.05, and that's called the coverage probability of your interval. So the coverage of your interval is going to be 95%. And this 95% refers to the repeated sampling, not to one specific interval. That means that if I repeat my experiment 100 times and I generate 100 intervals, 95 of them are going to be correct. And what I mean by correct is 95% of them, or in this case, we use 100 experiments, so 95 of these intervals are going to contain the true value. There will be 5 of them that will not contain the true value. Which one? We don't know. We don't know. So the 95% is a characteristic of the algorithm we're using to generate the interval, not a characteristic of any specific interval. So if I do an experiment and I get now an interval between 3.5 and 5, what is the probability that the true value will be there? 0 or 1. This 3.55 is maybe one of the good intervals, or maybe it's one of the bad ones, and I don't know. But I'm not very worried, because this 3.55 interval has been generated by an algorithm, a procedure that is right 95% of the time. So I'm going to go forward assuming that it got it right this time, but you never know that. So be careful here, because many times people say, oh, the probability that the true value is between 3.5 and 5 is 95%. No. The probability that the true value lies there is 0 or 1, and we don't know. But the procedure I use works fine most of the time, so I'm going to believe that it has worked fine now too. And that's the interpretation. So here you have the classical interval for the mean. This is asymptotically is the sample size is large enough. This is an approximate confidence interval, which depends on very known quantities: the sample mean, the sample standard deviation, the sample size, and the percentile of a t-distribution. That's it. So the probability, if you generate intervals following this algorithm, the probability that the true value is going to be there is 95%. Well, in this case, 1 minus alpha. And that means that 1 minus alpha, if you multiply by 100, in 1 minus alpha percentage of the cases, times 100 percentage of the cases, you're going to get a good interval. So here you have, this is your intervals. You consider alpha equal to 0.05, then the probability, 95% of all the intervals generated by this algorithm, if you want, 95% of them are going to be right. Which one? We don't know. If you use this algorithm and you get a specific interval, is that a good one or a bad one? Well, we don't know. Whether it is a good one or the bad one, we don't know. But the algorithm that generates this specific interval works fine most of the time, so I'm going to believe that has done a good job right now. And here you have an illustration of what we are talking about. So here I generated data myself. So when you generate data, you have a kind of gut look at the population, because I know that what is the value of mu, the true mean, is 0 because I generated it myself. I know what is the true values of sigma because I generated it myself, it's 1. And what we did is we went to this population and we took samples of 100 individuals. And for each sample, we constructed a 95% confidence interval. And here you have the results. The grace intervals, here you have the null, that's the true value of the parameter. The grace interval, we generated 100 intervals. The gray are correct because they cross 0, like this one over here, for instance. They cross 0. So 0 is contained in the interval. And the red ones are wrong intervals, in the sense that, as you can see with this one over here, it doesn't contain 0. And as you expect, we have here 4 mistakes. To be around 5. So 4 mistakes. So you use the interval 100 times, and 5 times, around 5 times, you're going to get it wrong. In real life, you never know if that specific interval you got is in the one of the red ones or one of the gray one. You don't know. But you move forward believing that it's one of the good ones, because the algorithm that generated is most of the time right. It's like when you step in a train, you know that there is a probability that the train will have an accident, but that probability is very small. The train will get you from point A to point B safely 95% of the time, 99% of the time. So are you going to have an accident? Well, you don't know, but you will get into your train and you will not be extremely worried, because it's something that works most of the time fine. Naturally, of course, in the case of the train, you will know at the end of the trip if you have gotten into trouble or not. In science, when you calculate an interval, you never know if it's a good one or it's a bad one, because you don't know the truth, and you will never do it. You may ask yourself, well, why we work with 95% coverage probability? Why not with 99? And here we repeat the same experiment. Here you have for the 95% confidence interval, and here you have for the 99% confidence interval. And as you can see with the 99, indeed, you made less mistakes. We got it wrong only one time, whereas here we got it wrong 4 times. Well, and why we don't use then always a 99, or even better, 99.999%? The problem is that if you look at this graph, maybe you will realize about something, and is that the 99% confidence intervals are larger, wider than the 95% confidence interval. And of course, you can always generate an interval that is always right. You have what is the average size of men in Belgium, and you say, well, it's between I don't know, 2 centimeters and 4 meters. You're going to be always right. You will have 100% coverage, but that's completely useless. So an interval that is not so wide is a very precise interval, but of course, the smaller it becomes, the higher the probability of getting it wrong. So you need to find a balance between the coverage probability and the precision in your interval. And it's kind of a standard nowadays in science to work with 95% confidence interval, but this is not a dogma. You can change that. And you may ask yourself, can I get it both? Can I get a large coverage probability and at the same time a very small interval? Yes, it's possible, but then you will need a larger sample size. You will need more data. If you want very precise conclusions with a high level, high probability of being right, then you need more data. If you have the amount of data fixed, then you would need to play with these two factors: more precision, less more probability of getting it wrong, larger probability of being right, less precision. So you will need to play with it unless you increase the sample size. And now we are going to introduce what is one of the most important concepts in statistics. I told you that there are 4 big schools of in statistics: the Bayesian paradigm, the frequentist paradigm, the likelihood paradigm, and the information theoretic paradigm. But there is something common in all of them. They debate each other in a very passionate way about what is the most sounded approach, the most sounded philosophical framework. They discuss a lot about that, but they have a common core. And that common is the likelihood function. And this is a concept that was, well, you can date it back even further, but it was a study formalized by one of the best statisticians in history, Ronald Fisher. And intuitively, the idea was, well, we are dealing with an estimation problem here, right? So we have this data set and we know the observations. We assume that they are emanating from a common underlying mechanism. We are assuming that we can model that common underlying mechanism using a probabilistic model. And this probabilistic model depends on certain parameters. And we want to make statements about that parameters because typically the scientific questions are formulated in terms of these parameters. Now, we have said, well, you need just to construct the formula of the data. That's a point estimate. And then we analyze several properties that we may want this estimator to have. It may be consistent, biased, it may minimize the mean square error, it may be asymptotically normal, etc. But how I generate this estimator, right? You are talking about the properties, but how I get one that satisfies these properties. And okay, you may try just to guess one. Right? You can try, so well, I'm going to consider this expression of the data. Let me see if it satisfies the properties. That's okay, but that's kind of inconvenient. I would like to have a way, a systematic way of generating good estimators. And Fisher proposed a method that is called the maximum likelihood methods. And it's a kind of method that allows you to generate good estimators, actually unbeatable estimators in the asymptotic sense. So this procedure not only allows us to generate estimators in many different situations, but these estimators, if you go to asymptopia, if you go to the land of large sample sizes, their maximum likelihood estimators really are extremely good. They are almost unbeatable. Now, what is a maximum likelihood? Intuitively, the maximum likelihood estimators select the value of the parameters in a model that give the observed data the largest possible probability. And think about it, that this is intuitively plausible, intuitively logical. So you do an experiment, you get some data. So you have seen that data. So that data should not be that weird, because weird, unlikely things do not happen, right? Or happen very infrequently. So if you do an experiment and you get a data set, probably that data set is not that unlikely. Maybe it is, and you just have seen a miracle. It can be, but it's reasonable to assume that that data set is not that unlikely. So what is a good guess for the parameters? Well, I'm going to choose the parameters that made the data more visible, in the sense of I'm going to guess the parameters using the values that made my data, my results, my data set, what I have observed, most likely. The probability of observing that will be maximized. And that's a very simple, intuitive idea behind maximum likelihood. Now, suppose that you have your data. Again, I'm not going to explain this here. You have your data set, and you assume that each of these observations emanates from an underlying probabilistic model. We are going to call it P of y, that's the probability of your data, P of y, and that probabilistic model depends on parameters. Now I'm going to consider that theta may be a vector. It's a vector of parameters. Like in regression, you have several beta effects, and you have the variance. So theta is a vector of parameters. So we are assuming that this is the probability of observing the data, P of y theta. That's a underlying probabilistic model generating my data. So the maximum likelihood, the likelihood of the data, is just the probability of the data, but you're going to look at it now in a different way. You're going to look at it not as a probability function, but as a function of the parameters. And we call that L. L theta y. So you look at the probability of the data now as a mathematical function of the parameters. And if the observations are independent and identically distributed, then this likelihood, which is just the probability of the data, but now you look at it as a function, as a mathematical function of theta, is just the product of the probability of the individual outcomes. We have seen that, nothing new here. So given a data set, the value of theta that maximizes this function is called the maximum likelihood estimator of theta. It's the value of theta that maximizes the likelihood, the value of theta that maximizes this, or the value of theta that maximizes the probability of observing the data. Now, this is now a mathematical model. You have a mathematical problem. You have a function a function of theta, and you want to find the value of theta that maximizes this function. This is a completely mathematical problem now. Now, typically, you don't work with the likelihood. You work with something called the log likelihood. You calculate the logarithm of the likelihood. Why you want to do that? Because the logarithm of a product becomes a sum. And it's a lot easier to work with a sum mathematically than to work with the product. And by the way, the value of theta that maximizes the likelihood also is the same value that maximizes the log likelihood. So we are going to work with the log likelihood instead of the likelihood, just for mathematical convenience. And as I said, the maximum likelihood is the value of theta that maximizes the probability of the data, is the value of theta that maximizes the likelihood function, or if you want, the value of theta that maximizes the log likelihood function. We call the likelihood is capital L, and we call the log likelihood with the small l. Now, if we want to calculate the maximum likelihood estimator, we need to maximize the log likelihood, this function. But this log likelihood is itself a random function. It's a random variable because it depends on the data. So you have a data set and you can draw your log likelihood. If you repeat your experiment and you get another data set, you will get a different curve. another log likelihood. Why? Because the data are random. So the log likelihood, these functions you're trying to maximize, they are themselves random variables. And we are going to estimate the parameter by maximizing these random functions. So we are going to get, of course, a random estimator, which is the maximum likelihood. But to study the properties of this estimator, this maximum likelihood estimator that we are going to use in logistic regression, in Poisson regression, in gamma regression, you're going to use it in hierarchical models. It's going to come back again and again and again. So if we want to study the properties of this maximum likelihood estimator, what you need to do is you need to study the properties of the functions this maximum likelihood estimator maximizes. So we are maximizing these log likelihoods, which are random functions, and we're going to study the properties of these random functions we're maximizing, because many of these properties later will translate into the properties of the maximum. And we're going to basically study two things of these random functions, two things of the log likelihood. We're going to study the derivative of these functions with respect to theta. We call that the score function. And we are going to study over here the score function, and we are going to study the second derivative of the log likelihood, and this is called the Fisher expected information matrix. Now, why we are studying this? Well, mathematically, I don't know how many of you remember your calculus course, but if you want to maximize a function, what you need to do is you need to calculate the derivative of this function with respect to the variable you're trying to maximize, and that derivative should be zero at the maximum. So you need to solve the equation, the derivative equal to zero. And that's essentially the score function. In statistics, this first condition, we call it the score function. Now, if you have a function, let's put an example over here. Let's assume that you have a function that is like this. Well, here you have the maximum of this function. Here you have theta. Here you have the maximum of the function. You're trying to find the maximum of the function. Here you have the minimum. And the derivative of a function is just the slope of the tangent that at a certain point. That's the derivative of this function, the slope of the tangent. And as you can see, at the maximum, the slope is zero. So the line becomes parallel to the axis of theta. But it's also zero at the minimum, right? So when you calculate the derivative, the score function, the derivative of the log likelihood with respect to theta, and you equal that to zero, and you find a solution, that may be a maximum, but maybe a minimum also of the log likelihood. And you need to differentiate if you are just dealing with a maximum of the minimum, because you certainly don't want a minimum. You don't want to estimate theta using the values that minimizes the probability of the data, right? You want the opposite. You want to estimate theta using the value that maximizes the probability of the data. So how do you know if it is a maximum or a minimum? Well, for that, you use the second derivative of the likelihood. You use the Fisher expected information matrix, because actually, if it is a maximum, then this matrix is going to be positive definite. Sorry, it's going to be positive negative. And if it is a minimum, it's going to be positive definite. But we are going to see this later on. So we look at now at, again, data that are independent and identically distributed. But as I said before, well, I didn't say before, but maximum likelihood properties can be extended also for the case in which you don't have IID. Okay, so let's calculate the score function. So it's the derivative of the log likelihood with respect to theta. Now, theta now is a vector. So the score function is going to be a vector itself. You need to calculate the derivative of the score function with respect to theta 1, the first component of theta, with respect to theta 2, the second component of theta. You need to calculate the derivative of the log likelihood with respect to theta p. So you're going to have now a vector. The score function is a vector with p components. Here you have the first component of the score function, the second component, etc. And you need to solve the score equation. So the only thing you need to do is you need to equal the score equations to zero. The zero is a vector now as well. So you need to equal this component to zero. You need to equal all components to zero. That's a system of equations. And the values of theta that solve that equations, they may be the maximum likelihood. You need to look also at the Fisher information matrix. Now you can look at the score function in a different way. Remember what is the score? The score, the log likelihood. You remember the log likelihood is just the sum of all these components. So it's the sum of the logarithm of the probability of each outcome. And if you look at that, then what you need to do is you need to calculate for the score function. What you need to do is you need to calculate the derivative of the score function with respect to theta. And that essentially means that you need to calculate the derivative of a sum is the sum of the derivative. So you need to calculate here also the derivative of these components with respect to theta. So the derivative of each individual, the probability of each individual outcome with respect to theta. And that's what we are going to do here. So you can write the score function in this way over here, but it is useful sometimes also to write it in this way over here, where this SI is the score function associated with the first observation, if you want. And this is just the score function. What about the second derivative? So the second derivative is, well, the second derivative of the log likelihood is the first derivative of the score. So you need to calculate now again the derivative of the score function with respect to theta. And now this is a matrix. So it's the second derivative of the log likelihood with respect to theta. And now this becomes a matrix. And again, if you calculate this derivative here, you need now to calculate again the derivative of this term with respect to theta. And this is what you get, the sum of this derivative. But this is now going to be a matrix. Each component here is a matrix. You are just calculating the derivative of the logarithm of the probability of each observation with respect to theta 2 times. It becomes a matrix, and we call that matrix the Hessian matrix. Is given over here. That's the Hessian matrix, and we are going to see a lot more about it. Okay, fine. What is then the Fisher information matrix? Well, the Fisher information matrix is the minus the expected value of the Hessian matrix. Or do you want minus the expected value of the second derivative of the log likelihood respect to theta? That's called the Fisher expected information matrix. And again, if you look at what is the Hessian matrix, we saw it over here. If you look at what is the Hessian matrix is this sum over here. So if you calculate minus the expected value here, essentially what you need to do is to calculate minus the expected value in this sum over here as well. And if you do that, this is the other way you have to write the Fisher expected information matrix. Now, if the data are independent and identically distributed, then all these individual expectations here are going to be the same. Why they are going to be the same? Because essentially this P here is the same for all individual observations. They are all being generated by a common underlying probabilistic model. So the probabilistic model that generated Y1 is the same as the probabilistic model that generated Y2. And then when you calculate this expected value, you get the same. So all then are going to be the same. So the expected Fisher information matrix over here can be written as N times I1. And what is I1? I1 is the expected Fisher information matrix for the first observation. It's all of them, for every observation, the expected Fisher information matrix will be the same because they are generated by the same mechanism. And you are summing over n, so this is the result. So here you have the expression for I1 is just the expected Fisher information matrix you can consider from one observation. The first one, the second one, doesn't matter, from one observation. Okay, we are now going to see some properties of the score function. Suppose that the model is correct. Suppose that you got right the data generating mechanism. And what means that? That means that there is a value of theta, so that when you plug it in your model, this is really the true way the data were generated. So there is a value of theta 0, that when you plug it in your model, that's exactly what is going on. Well, you can show that the expected value of the score function, when you evaluate it in the true value of the parameter, the expected value is 0. So remember, the score function is a function of the data, so it's random. So the expected value on the data, so you get all these random functions there. When you just calculate the expected value of all these functions, the average of all these functions with respect to the data, that's 0. Now, when you evaluate it in theta 0, of course, for every experiment, you get just the score function becomes just what you get a function that depends on the parameters. So you're looking at this log likelihood as a function of theta. So now when you repeat the experiment, you get different functions. And if you evaluate each of these functions now in the true value of theta and you calculate the average, then you get 0. That's what we are saying over here. Now, what is the variance of the score function evaluated on the true value? Well, you remember what the score function is. Well, you go back here, you remember that the score function was just the sum of these individual score function for each observation. So the variance of this, given that the data are independent, are going to be just the variance of each of these elements over here. And that variance you have here, that variance, well, if the individual score functions are going to have also mean 0, you can show that that variance can be written in this way. So the variance of the score function is just the sum of these expected values having the products of these two terms over here. And actually, if the data are identically distributed, then you have something similar that you had with the Fisher expected information matrix, is that each of these individual components are going to be exactly the same if the data are IID. So the variance of the score function is n times the expected value of one of the elements. You don't need to go through all the i's, one is enough. So here you have the score function of one observation, which is just the derivative with respect to theta of this distribution, which is the same for every observation, so you can consider one. And then if you transpose that and you multiply by itself and you calculate the expected value, this is then multiplied by n, this is just the variance of the score function. And there is something, when the model is correctly specified, there is something called the so-called information matrix inequality, which essentially means that you can calculate the variance, this expected value of the double product you have over here actually equals the Fisher expected information matrix of one observation. So is equal to this term here. But this is true only if the model is correctly specified, which is an assumption we frequently made. So the variance of the score function can be written in two equivalent ways. You can write it using this product over here, or you can also do it as the variance of the score function as the expected value of this Fisher expected information matrix. Now you can show that the score function, you have the number of properties over here. For instance, asymptotically, the root square of n times the score function. What is the distribution of that when you evaluate it in the true value of the parameter? Well, that follows a normal distribution with mean 0 and variance covariance matrix I1. Or you can write that in an equivalent way. When the sample size is large, the score function follows a normal distribution with mean 0 and variance the expected Fisher information matrix, which is the one we saw here, this minus the expected value of the Hessian evaluated in the true value. So if you want to make inferences for the score function, you essentially need an estimator of the Fisher information matrix, expected Fisher information matrix. And how you can estimate this parameter? Well, you know that the Fisher information matrix is the expected value of the Hessians, right? So one possibility is you plug here an estimator of the true parameters. So this is what we call I3. So you plug here just an estimator of theta and you get an estimator of the Fisher information matrix. Another possibility is you forget about the expectation altogether. And what you do is you just estimate the Fisher information matrix, forget about the expected value, just consider the Hessian and plug here an estimator. That's called the observed information matrix. This is the Fisher information matrix when you use the expected value. Over here, when you don't use the expected value, is called the observed information matrix. You just plug in an estimator of the Hessian. And this is what we call I1. And then you can also use this cross product we saw before. This emanates directly from the information matrix equality we saw before, that essentially you can use this cost product over here. This is also the variance of the score function we saw before. Forget about the expected value, just consider the sum, plug in here the estimator, and that's what we call I2 here. So we have three possible ways to estimate the variance of the score function. And the only thing you need is a consistent estimator of theta. It doesn't have to be the maximum likely estimator, just a consistent estimator. And as I said before, minus the Hessian evaluated in an estimator of theta is called the observed information matrix. Frequently, you evaluate it in the maximum likely estimator, but that's not always the case. Okay, and we're going to enter now in the last part of the lecture, the theoretical part. This is called the Cramer-Rao bound. So what is that? It's called sometimes the information inequality. And you will understand later on what we are seeing all this. Well, the information inequality gives a lower bound for the variance of an unbiased estimator. So if you have an unbiased estimator, if you're going to say, well, I'm going to consider only unbiased estimator, what is my best choice? Well, you would like the unbiased estimator that have minimum variance, right? The ones that have the smallest variability. By the way, in the class of unbiased estimators, the one that has the smallest variability is the one that minimizes the mean square error. So in the class of unbiased estimator, minimizing the variance is equal to minimizing the mean square error. Why? Because the bias is zero, right? That's why they are unbiased. So if you're dealing with unbiased estimator, you would like to have one that minimizes the variance. Well, the Cramer-Rao bound give you a lower bound for the variability of unbiased estimators. And when you have unbiased estimator that achieve that a lower bound, then it is unbeatable in the class of unbiased estimator. You cannot find one better, because that will be the bias estimator that minimizes the mean square error. Okay, now such an estimator achieves the lowest possible mean square error. However, sometimes it doesn't exist. Sometimes when you consider the class of unbiased estimators, you don't have one that achieve the Cramer-Rao lower bound. By the way, when a bias estimator achieves this lower bound, we say that it is efficient. It's the best you can get from an unbiased estimator, one that achieves the Cramer-Rao lower bound. You cannot get better than that, and we call them efficient. Well, what is the Cramer-Rao bound? Well, the Cramer-Rao bound says the following. Suppose that you have an unbiased estimator. It's a function of the data. We're going to call it T of y, right? And it's an unbiased estimator that of certain function of theta. We call it psi of theta, right? So let T of y be an unbiased estimator of a vector function of the parameter psi of theta. What is psi? Well, in principle, can be a general function. Now, the Cramer-Rao bounds says a minimum for the covariance matrix of your estimator. So the Cramer-Rao inequality says that the covariance of T is always larger or equal than this expression over here. That's an interesting thing, because here you have the inverse of the Fisher information matrix. And here you have the Jacobian of your transformation, because remember, you have a transformation of the parameter psi of T. And this is the most general form you can have for the Cramer-Rao inequality. So essentially here, G of theta is the Jacobian matrix, is the matrix of the derivative of your transformation with respect to the parameters. And this is an inequality between matrices. Don't forget, this is a variance covariance matrix, this is a variance covariance matrix. And when I'm going to say that the matrix A is larger than the matrix B, I'm going to say that it's understood that the difference between these two matrices, I minus B, is positive semi-definite. And if you don't know what is positive semi-definite, please go to Google and try to get that concept. It's just linear algebra. I know it's a little bit theoretical, but try to get some kind of conceptual understanding of it, because we are going to be professional statisticians. So we are professional statisticians, so we are supposed to have a deeper understanding of the methods we use, right? So an special case of this is when you have just you are just trying to estimate theta itself. So your estimator theta hat, let me put it here, that estimator theta hat, which we are calling T of y, that estimator is trying to estimate theta itself, not psi of theta, but theta itself. In that case, of course, psi of theta is just theta. And in that case, the Cramer-Rao inequality over here translates into something a little bit simpler. So the covariance of an unbiased estimator of theta is always, the covariance matrix, greater or equal than the inverse of the Fisher information matrix. So if you have an unbiased estimator that has variance covariance metric equal to the inverse of the Fisher information matrix, you have gotten it. That's the best you can get, because that's the best estimator, the one that has the smallest variability, the one that minimizes the mean square error. So the inverse of the Fisher information matrix is, if you want, kind of the holy grail here. If you have in the class of unbiased estimators, if you get one that reaches that lower bound, the variance covariance matrix is exactly equal to the inverse of the Fisher information matrix, then this is the best you can do. And now we finally can go to what we wanted to study, the maximum likelihood estimator. Now, this is the maximum of the log likelihood, these random functions that we have studied until now, these random functions that have these properties that they are asymptotically normally distributed, they have mean zero when you evaluate it in the true values, the parameters, variance zero, etc. Now, you we maximize that function and you get an estimator of theta, what we call maximum likelihood. Now, how good is that estimator? Is consistent, is unbiased, is minimizes the mean square error. How good is that estimator? And remember, intuitively speaking, what you're doing is you're estimating theta using the values that made the data more visible, using the variable that maximizes the probability of seeing this outcome, this data set. So it's a very intuitive idea. And actually, it is a very pretty good estimator asymptotically. So when you are in finite samples, it doesn't have necessarily any optimal property, in the sense that you may have other estimators that beat him because they have, for instance, a small mean square error. They concentrate more closely to the true value. So in finite samples, the properties of the maximum likelihood estimators are not optimal necessarily. They may be still pretty good, but the properties of the maximum likelihood are asymptotic properties. So if the sample size is large, they possess a whole bunch of nice properties. They become, in asymptopia, they are the king. In finite samples, that may not be the case. And asymptotically, well, the maximum likelihood estimator is consistent. So it means that if you use the maximum likelihood estimator, you can get as close to the true as you want. You just need more data. If you have data enough, you can get as close to the true as you want. They are also efficient. So they are asymptotically unbiased, and their variance covariance metric exactly equals the inverse of the Fisher information metric. So they minimizes the mean square error. You cannot get better than that. So asymptotically, they are consistent, they are unbiased, and they are efficient. They have the smallest possible variability. But more than that, asymptotically, they are also normally distributed. So if you have enough data, if your sample size is large enough, the maximum likelihood is really a very nice estimator. Consistent, unbiased, efficient, asymptotically normal. Difficult to get better than that. But again, this is large sample sizes. It's in asymptopia. So let's explain these properties a little bit more. What is consistency over here? Well, under general regularity conditions, you need to have some conditions for your likelihood. I'm going to give you an idea of what these conditions are, but they are indeed very general. So many models, these conditions are satisfied, but not always. Not always. In some situations, they are not satisfied. But generally speaking, under general regularity conditions, if the data were really generated by these models, so if you have a value of theta, we call it theta naught, that when you plug it in your model, then this is it. This is the true data generating mechanism. If you got your model right, when you have that, we say the model is correctly specified. There is a value of the parameters, theta zero. When you plug it in your model, this completely describes the data generating mechanism. If that is true, and you have a sufficiently large number of observations, then you will see that, well, actually, when n goes to infinity, the maximum likelihood estimator of theta will go to theta zero in probability, will be consistent. The probability, you will get as close as you want as theta zero. So for any value epsilon, the probability that theta, the maximum likelihood, will be further from the truth than epsilon, that probability goes to zero when n goes to infinity. So that's consistency. And it is efficient and asymptotically normal. We call it root square n consistent over here because when the sample size is going to infinitive, and we construct again this random variable, root square of n times the maximum likelihood estimator minus the true. Well, when n goes to infinitive, this random variable over here, its distribution, it gets closer and closer to a normal distribution, which means zero, and variance covariance metrics, the Fisher information metric of one observation to the power minus one. So the inverse of the Fisher information metric for one observation. Or you can rewrite this in another way, which is easier. So the maximum likelihood estimator of theta asymptotically has a normal distribution, which means the true value you're trying to estimate, theta zero, and then the inverse of the Fisher information matrix. And remember, the inverse of the Fisher information matrix, or the Fisher information matrix, is minus the expected value of the Bayesian, now evaluated in the true value over here. And if you want to make now confidence intervals calculate p-value, of course, you will need to estimate this guy over here. You will need to estimate the inverse of the Fisher information matrix. And we saw it in the previous slide. You can estimate that in 3 different ways. You can use the estimator I1, I2, or I3. All of them will give you similar results, generally speaking. Now, I told you that all these nice properties, the maximal likelihood estimator will be asymptotically unbiased, asymptotically efficient, consistent, normally distributed. All these nice properties happen under general regularity conditions. What does that mean? Well, these general regularity conditions essentially means that for instance, the first thing is that your distribution, your probabilistic model should be identifiable. And that means that different values of theta produce different distributions. If you have 2 different values of theta producing the same distribution, then you get into trouble because you say the model is not identifiable. You would not be able to differentiate the model using theta 1 from the model using theta 2. The data would not be able to differentiate between these 2 thetas because they lead to the same probabilistic model. The other property you need is that the range of the data cannot depend on unknown parameters. So the range of the data should be independent of the parameters. The true parameter must lie in the interior of the parameter space. So for instance, you are dealing with a variance and you want to use the maximal likelihood estimator, the true variance should not be 0 because 0 lies at the border of the parameter space. If you are trying to calculate the maximal likelihood estimator of a probability, it should not be 0 or 1. The true probability should be strictly between 0 and 1. And the number of parameters must not increase with the sample size. So when I start gathering more data, the number of parameters should not continues to increase. Typically, it should be the same, should be constant. But you can generalize this to a situation in which it increases, but not too fast. We are not going to see this into detail. Now, for the properties of the maximum likelihood, suppose that you have the maximum likelihood of a parameter vector of parameter theta, and now you want to estimate a function of the parameter psi of theta. Well, the maximum likelihood of psi of theta is what you would expect the size and evaluated in the maximum likelihood estimator of theta. So the only thing you need to do is you just need to plug in the maximum likelihood estimator of theta, and you will get the maximum likelihood estimator of psi of theta. And then you can, you also will have using the delta method that the maximum likelihood estimator of psi would also be asymptotically normal, which would mean, well, psi of theta, and which with variance covariance metrics, well, then you will have the Jacobian times the covariance matrix of the maximum likelihood estimator of theta times the transpose of the Jacobian, and taking into account that the covariance, asymptotically, the covariance matrix of the maximum likelihood estimator is the inverse of the Fisher information, then you get this expression here. And if you want now to make inference for psi of theta, the only thing you need to do is to estimate this guy over here. And again, you just can plug in here the maximum likelihood estimator of theta, and you will get an estimator, or you can just use the previous estimators we saw. And the maximum likelihood estimator is also invariant to one-to-one transformation of the data. So you transform the data, you will get exactly the same value. Okay, now how do you calculate it in real life? How do you calculate the maximum likelihood estimator in real life? Now we are going to use a maximization method called the Newton-Raphson method. This is what R does, or SAS does, or many other routines do. So suppose that you have a parameter value at an iteration of the method. Suppose that you're doing an iterative process. That's what we're going to do. And at step k, you have this value for the parameter theta k. Now, what you're going to do is you essentially, to find the maximum likelihood estimator is just to solve the square equations, right? You need to equal this to 0, this equal to 0, and find the value of theta. And that's your maximum likelihood estimator. You need later to check the Hessian. But essentially, what happened here is we are going to approximate the score function S of theta using Taylor expression, say Taylor series expansion. And we're going to expand it to the first order. So you are going to approximate the score equation by a linear function. And this is the expression for the Taylor series expansion. So here you have the score function evaluated in the value you got in the previous step. There you have, again, the Hessian evaluated in the value of the previous step, and then you have theta minus the value you got in the previous step. And what you're going to do is you're going to evaluate this to 0, and now this is a system of linear equations, right? This is what you get here, a system of linear equations in theta. So you need to solve this equation in theta. And if you apply a little bit of linear algebra, this is what you get. When you solve this in theta, you get the new value for theta, which is going to depend on the value you had at the previous step. And the new value in theta, so at the step k plus 1, that will be the value, the way to calculate the theta k plus 1 based on theta k. And as you can see here, we get from the Newton-Raphson procedure, we get automatically the inverse minus the inverse of the Hessian. And don't forget that minus the inverse of the Hessian is an estimator of the Fisher information matrix. This is the called observed information matrix. The expected value of the minus the expected value of the Hessian is the Fisher information matrix. So the minus the Hessian is just the observed Fisher information, and that is something we can use to estimate the variance covariance matrix of the maximum likelihood. So the procedure gives us two things: an estimator, the maximum likelihood estimator, but also the variance covariance matrix of that estimator. It's perfect. We get two for the price of one. And this is called the Newton-Raphson algorithm. It's an algorithm that we use to solve the scores equation. And what you do essentially, you approximate the scores equation with a linear equation, and you solve the linear equation. So here you have a representation of what we are doing. Suppose that you're trying to find in which point this f of x function over here crosses the x-axis. So you're trying to find a zero of that function. We call that the root of the function. You're trying to solve the score equations. So the score equations, we call the root of the score equations is the value of theta that makes the score equations equal to 0. And what you are doing, what the Newton-Raphson does is you have a value x0. This is the value that you need to get somewhere. But once you have that initial value, what you do is you calculate the tangent. You approximate the curve by a line. This is the tangent of this curve at point x0. And now you solve the equation, the linear equation, where this line crosses the axis here. And then you go up and you evaluate the function. You repeat the procedure again. Once you get the solution, the first solution over here, using the tangent, then you go and you evaluate it again in your function. And now you calculate the tangent again, but now at this new point. And so you get an update, another x2, and you evaluate the function. And you continue this process several times. And as you can see, looking where the lines cut the x-axis, you get closer and closer to where the curve actually crosses the x-axis, so to the root of the equation. That's Newton-Raphson. Now, there's also another procedure called Fisher scoring. And the only thing Fisher scoring does is it replace the Hessian, go to the algorithm where you have the Hessian, it replaces the Hessian with the expected value. But then, of course, you need to have a theoretical expression for that expected value. But if you have it, then you can program that. And instead of using the Hessian, you use the expected value of the Hessian. That is another algorithm called the Fisher scoring. Now, the Newton-Raphson has a number of nice properties. For instance, convergence is quadratic. And that means that as the methods get closer and closer to the root, to this real zero, then the difference between the root and the approximation is squared at every time. So it accelerates if you want. Now, it may fail. You may have situations in which the algorithm just get into trouble. When it can get into trouble, for instance, when you have a stationary point, when the Hessian becomes singular. Why is that a problem? Well, remember, in the algorithm, you need to calculate the inverse of the Hessian. So if the Hessian becomes singular, that inverse doesn't exist. And then you may get into trouble. It may get into trouble if you give a poor initial estimate, because you need to start with one value, one theta. And once you give me one theta, the algorithm starts iterating and it converges to the truth. Now, if you start very far from the root of the equation, then you may get into trouble. And if the Hessian is not well behaved in the neighborhood of a particular root, then of course the method may also diverge. So there are some situations in which you may fail to get convergence. But in general, the Newton-Raphson algorithm is a very good algorithm. And well, here we have an example that we have analyzed. I I will not go into details here. I will leave this for to you to go through it as a homework. It's just a very specific example where we have a binomial distribution and we are going to calculate the maximum likelihood estimator of the probability. So it's the conceptual framework is you have a surgeon that operates 12 patients and he gets 9 successes. And you want to estimate the probability of success for that specific surgeon. And it's just an application of all the concepts we have seen today. So I advise you to go there and to go through this example and to try to get an understanding of all this. Well, I know this was a challenging lecture. There's a lot of theory involved. I find it myself particularly fascinating, the study of all these properties. You are going to see all this later on when we work with the models, because we are going to use maximum likelihood estimators. You cannot use least square anymore. I mean, the linear model is a special case of GLM. So when you're dealing with linear regression, you cannot use a least square, which is equivalent to maximum likelihood. But when you move away from linear regression, you start talking about Poisson regression, logistic regression, gamma regression, the least square methods, at least in the classical formulation, is not what we are going to use. We are going to use the maximum likelihood estimator. We are going to see the Bayesian. We're going to use it to estimate the standard deviations of the maximum likelihood estimators. We are going to see the Newton-Raphson algorithm working in practice. That's what R uses to maximize the likelihood to solve the score equations. We are going to see all these properties in action. So it's good to have a good understanding of all these methods, not only for GLM, but also for whatever or many other courses you're going to see later on. So thank you for being here today, and we are going to stop here.